practical of natural convection. Okay, and yes, we are taking the help of the Amrita University. This particular simulator is made up by this Amrita Vishwavidyapith. Okay, and we are taking the help of this virtual from this one virtual lab. Okay, so the structuring is like this one. And what is the aim of this practical? Let's see. In this one, we are going to find out to determine the overall heat transfer coefficient, means the U, at the surface of a given vertical metal cylinder by a natural method. And the second, to determine the value of a Nusselt number. Actually here we are interested to calculate the H value. Okay, rather than the U, we are calculating what is the H, the heat transfer coefficient for the surface of a given vertical metal plate cylinder. Sorry, plate no, it's a cylinder. Okay, and then once we calculate the value of H, the next to determine the value of Nusselt number. Also, once we know the H, definitely we can easily calculate what is the Nusselt number for this case. Okay, now what is the apparatus? How the apparatus is look like? So it is look like this one. It having a hollow cylinder made up of a metal. In this simulator, we have the aluminum material, copper material, steel material, iron material. So you can change the materials too, as well as there is a, you can change the length and the diameter also of the cylinder. So this cylinder having a coil. Inside this cylinder, there is a coil which heated this cylinder. And now this cylinder is fixed in the hollow rectangular tube. Okay, means this one is placed in the rectangular tube. So there is a hollow cylinder, a hollow rectangular duct. Okay, so it is there, and we are fixing the hollow metal cylinder which having the heater. You see here the heater inside here. Okay, then you can see hollow metal cylinder. So this is the yellow boundaries show the hollow metal cylinder, and this is the structure of the wooden hollow rectangular tube. And they give the various they measure the various temperatures. So they measure the inlet temperature of the air which is in from the bottom, and also they measure what is the air from the out, that is measured by T6, I think, yes, T5, sorry. Okay, so inlet temperature of the air measure, outlet temperature of the air is measured by T1 and T5, and 1, 2, 3 and 4 thermocouples are placed on the surface of a tube, which is measure the average temperature of the surface of a cylinder. And inside it, as it is a heater, it means it generate heat. Heater is generate the heat. Heat is given to the cylinder. Now the surface, the cylinder surface, and the air which is be there surrounding the cylinder, there is an exchange of heat. And as we are not using any blower here to flow the air, means by naturally the air comes from the bottom side, it goes from the top side. Why this is happened? Why it is enter from the bottom and why it is go out from the top? The reason behind, as we know that the heat, the air, it get heated. Once it is heated, then the density of the air goes down, and as the density goes down, means it is in a lighter weight, and because of that one, it will try to move up. Why it is up? Because another dense air is try to move here. It replaces the hot air by a cold air, and such a the pattern is set. So air get in here, it get out, in, out, like this one. Okay, so simply here, so in this one, what we want to calculate, we want to know what is the value of H in this situation. So if this is the condition, what will be the value of H? That is the heat transfer coefficient. Okay, and that can be calculated by a simple equation, that Q is equal to H A delta T. If I know the A, if I know the delta T, if I know the Q, I can easily calculate the H. And if I know the H, if I know the D, if I know the K, then I can calculate I can calculate the Nusselt number. Okay, so it is very very simple. The practical, uh, don't worry. But yes, in the while writing the practical, you just write the aim, this one, write down the details about the apparatus. You can draw the diagram of it, okay, as it is mentioned. Write down the theory of it, okay, and then write down the formulas here, okay, to calculate the okay, you can take this part 1, equation 2, okay, then we use these equations. So everything you just write it, forget about application, but up to here you have to write theory. And then once it is over, then you can click here, you click here, a procedure. Okay, so here it shows the procedure of a simulation, how to perform the practical. So they mention, choose the material, side of the wooden box, height of the wooden box, diameter of the cylinder, length of the cylinder, thickness of the cylinder, and height knob, as well as the power and temperature indicators. Okay, no need to write this part, but yes, you have to write the procedure here. Okay, and after the procedure, you just write down or draw this table. Okay, the metal that you use, the voltage that you set, the current that you set, and the four temperatures T2, T3, T4, T5, and the two inlet and outlet temperature T1 and T6. Okay, and then the calculations part, we can calculate the value of Q, how much it is given by the heater. And obviously as the air is flow between the channel between the wooden box and the cylinder, so definitely there is an exchange of it between the surface of the cylinder and the air. And as there is no heat out from the rectangular duct, because it is made up of the wooden, so wooden is a good insulator. Okay, so we can know say that we can calculate the Q. How we can calculate the Q? Here we can calculate the Q with the help of the voltage and the current. So V stands for the voltage here. Remember this part. I is the current, and that can be calculated by V into I. And where from these terms, if you see this picture, then you see here there is a voltmeter and there is an ammeter. So once you on it, then you can set the volt and ammeter by clicking here. Okay, I will tell you in detail how to do the perform the practical and all. But yes, we from this way we can calculate V into I. It will give the Q. Okay, so now the area can be calculated with the help of this one. Once you set the D, the diameter of the tube cylinder, and into the length of the cylinder, it will give the surface area for the heat transfer. And the delta T value can be calculated with the help of this formula. And the formula is T2 plus T3 plus T4 plus T5 by 4. It means, yes, here, 1 second. Yes. You see here, whatever be the thermocouples which we have, 1, 2, 3, 4, that one. The average of the surface temperature minus the average of T1 and T6. Okay, are you getting my point? So that way you just have, yes, uh, you can calculate the delta T. So average temperature of a surface minus inlet plus out by 2 average temperature of the air. That will give the value of delta T. It's very simple. Okay. Now once you calculate the delta T, once you calculate the Q, then what is the remaining? The remaining is what? Again we have a simple equation. Q is equals to the H into A into delta T. We know that Q is equal to H into A is the surface area into the delta T. So H is, we calculate, we can calculate the H as we know the Q. This is the V into I means Q upon A delta T. So there is a some what we call the, we change the terms and we write in terms of H. So we get the value of H with the help of this formula. Voltage into the current, it will give the value of Q. A is from this one and the delta T is from this one. And once you calculate the value of H, you can put it here in this formula to get the value of Nusselt number. Okay, this N is what? It is the Nusselt number, N suffix U. Okay, here it is represented by N. So that is the Nusselt number. It is HL by K. H is what? H is the heat transfer coefficient, and yes, the L is the length of it. Upon the K is the conductivity of a fluid. Okay, so with the help of that one, you can easily calculate the Nusselt number. Yes. Now L is stands for the characteristic length. Okay, you just mentioned here. L is nothing but it is a characteristic length. So you calculate the characteristic length. Okay. Okay, fine. So is it clear to all?
Yes, sir.
Yes. So you go first theory, write down the theory, and then go for the procedure. You just write the procedure, write the table, and then do the calculations. And then the result is here. The heat transfer coefficient is this much, and the Nusselt number is this much. Whatever, and yes, the value of K you should take here. It is K is equal to 0.024. Okay, is the thermal conductivity of the air. Okay, here L is the length of the cylinder. Sorry, so that rather than characteristic length, you can see here it is the length is directly given. Okay, in length. Now we will go for the simulator. Now for the simulator, don't click on this one, because again once you click it, let's check whether it is comes the same one or it is a different. No, it is not mentioned here. There is some problem here when you are clicking the simulator. So that's why I'm giving the another link to you. Okay. So first link, it will means I just tell you. So once you click on this link, okay, you just go for the theory and the procedure one. Okay, go for the theory and the procedure. So that is a writing work. And now the second one, if you click on this one, then you will get a simulator here. Directly you can go here. Is that clear? Any difficulty here?
No, sir.
Yes. Okay. Thank you. Now let's see how to perform the experiment in a virtually. Okay. So see, this is the apparatus, and this is the voltmeter. This is the current. So it will show you here some value of voltage and the current. This is the temperature indicator. You can see the temperature from 1 to 6. 2, 3, 4, 5 is of temperature of the surface of the cylinder. 1 and 2 is the temperature of the air inlet and outlet. Okay. Now, how to perform the experiment? So is it visible to you, all of you? Can you visible this part properly?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Good. Now you can see on the right hand side here. So choose the material. So first we need to choose the material. So if you click on here, you can see there is a list of the material. It might be the aluminum, copper, iron, silver, anything can be choose. It is on you. Okay. For our calculations, we are interested to choose the aluminum, and then you can choose the copper. Okay. So we will take a two material, and we will change the diameter of these two material too. Okay. So aluminum is what means this is made up of aluminum. You can be choose copper. Okay. So this is the copper tube, or you can choose the iron. See here the color get changed, it can be iron, or you can choose the silver. So this is the silver cylinder, or you have a steel. Okay, anything, any material can we choose. So now for our practical we will choose the aluminum and copper, because maximum time we are dealing with that one. So let's see aluminum. Okay, the first I choose the aluminum. Then you can see here there is given width of wooden box. So this is a wooden box, okay, in which we fitted the cylinder, hollow cylinder, and in the hollow cylinder we have a heater. Okay, I will show you after that one. Once we have, see here, show a cross section. Once you click here, you can see here. So there is some, here is the a coil. Okay, this is the cylinder. Now I just take a cross section of it, and now I can see inside what is there. So here is the coil which is heated this cylinder surface, and what, see here, T2, T3, T4 and T5, it measure the temperature of a surface. And the T1, this one means T1, and T6 is the outlet temperature of the air. Okay, now what happened? First, what we do, first we kept this reading as it is. You can change it, depend. But now, for our purpose, just to know the how to perform this one, so we choose the readings as it is. Don't worry. And now, once I select the material, and then just for my to know what exactly there is, I just have the cross section, or no problem. You can see the result here. Heat transfer coefficient is 0, Nusselt number is 0. Okay, but when you are doing a calculation, so don't take the result from here. I again repeat it, don't take a result from here. You just do the calculations, and accordingly you choose what is the value of h and what is the value of n, and then see whether it is similar to that or not. Okay, is that clear now?
Yes, sir.
So the diameter, everything, yes, everything we kept constant as it is, whatever mentioned there. Okay, if you set it, reset, see here, whatever be the value we kept as it is, and we just have the aluminum as it is. Now we start the power. Okay, once you start the power, then we need to adjust the voltage and the current, because accordingly we can have change the value of q. Okay, now for first, on here, you can't operate from here, but yes, first you need to on from here. Yes, it get on. Okay, now what happened, the air comes out, come in from the bottom. As it is a hollow structure, it will go up, and then somewhere it goes uh, out from the duct. Okay, so this is the pattern of flow of air. The arrows which is shown in the by the white color, all these are the air motion, and the direction is from down to up. Now what you have to do, you have to adjust this voltmeter and ammeter. So let's first I adjust it by say 120 volt. I place, and the current is zero point 0.4 by now clicking the knob here. Okay, you can down here, you can click here, the knob get like this one up to the 120. You can adjust it up to the, I think, yes, it is around, let's see how much it get, up to the 300. But yes, you just kept it for say 150 to, yes, it is okay. The 150 is the current that I have placed, but depend on you. I'm not say that you, I am not insist that you do this same one. Okay, then next, once it is over, then you see here, the temperature gets set at 148, 150, 154, 156, and then there is a, here is the temperature 36, and the inlet temperature is here T1 30. Even you can see here the voltage in and the current is mentioned. You can see the which temperature you are measuring. So now it is T1 30. Click on this knob. It is show the T2 148. Note down in your here. Um, Note down here. Okay, in this in this block. Then click on here T3. So again you can note it here. Okay, so you, aluminum is here, voltage we kept it is 150, current showing it is 0.64, and then we measure the T2, T3, T4, T5 temperature of the tube, and then we can measure again with the help of this knob by changing the knob position. You see it, the T6, 36, T5, 156, like this one. Everything you kept here. Okay. And then once we collect the data, this data, the voltage ammeter and this all the six temperatures, then we go for the calculations. And for the calculations, we need the four temperatures and these two temperatures. And we do the calculations like V into I is nothing but the Q. V into I is Q. Area pi into D into L. Where what is the D? What is the L? It can be shown here. Okay, the height is L 75. No, sorry. Length of the cylinder is 55. Diameter of the cylinder is 7. So don't take this side. You have to take this side. The length of the cylinder 55 centimeter. Diameter is 7. You convert centimeter into the meter, and then you just put it here, D into L into pi. It will give the surface area in meter square. Okay. The average temperature, again with the help of the table that we have. Yes, with the help of this table, we put it the value of T2 plus T3 plus T4 plus T5, take the average of it, minus T1 plus T6, take the average of it, and it will give the delta T. Okay. Then we use the formula, this one. H is equal to V into I, nothing but the Q upon A is the surface area. This one into the delta T, you will get the value of H. Put it here, and then the value of Nusselt number. Calculate H into the length of the pipe into the K is the conductivity of the air, which is mentioned here. Okay, this is the conductivity of the air, thermal conductivity. Okay, you just place these the values there, and then you calculate the Nusselt number. Is it very simple?
Yes,
All of,
sir.
any problem while doing this simulation? Yes.
No, sir.
Okay, I again repeat how to start it. Okay, I just reset it again. Okay, now first thing, choose the material. So I'm choosing aluminum, is okay. Everything I kept as it is. Then I start the power, and then I directly go here to adjust the voltage. So I kept it voltage up to the 150. Okay, and then I stop. Don't take a reading because you see here up to the 20 minutes. It's required for a steady state. Once the steady state comes, then we can uh, take a reading. Now you see there is a continuously fluctuation of it, and now after the 20 minutes, what you see, this gets stopped, and even you can check the temperatures. All are get set. Means the steady state occur. And now on the steady state, we are using that equations to calculate. And that's why it is very important for get a steady state. Okay. Now, once this clock shows it is 20, means everything is now it is correct. Now everything is over. We can measure voltage 150. You can write current zero point 0.6 in the table. Then yes, you can click here by to and fro of the this knob. Okay, so if you click here, you can get T1 measure 30, click T2 148, again click T3 150, T4 154, T5 156, click 36. Okay, and if you want to reverse one, then you again you can just click here left hand arrow, the knob get round. Okay, and then also you can measure these values. Okay, you just note down these values and then do the calculation. Now you see here, uh, here it is show the calculation. Nusselt number is 78.41 and the heat transfer coefficient is 2.5. Got it? Yes.
Yes, sir.
Any problem here?
No, sir.
Okay. Now
No,
check
sir.
the another material. Okay, but before that one, what we do, we just adjust the diameter. First we adjust the diameter more and then less. Okay, so reset is again. Now what I'm doing, taking the aluminum as it is material. Voltage I kept 150. The current accordingly it will be the zero point 0.6. Okay, and now what I do, I just change the diameter of this tube. I just change the diameter of this tube. say from the 7 I just take it up to the 8. Okay, and then again do the same procedure. I just start, I adjust the voltage up to the 150 because the previously I have taken the 150. That's why. If you take the 120, then you should, for this case also, you should take 120 itself. Now, as I am taking a 150 for the previous one, so here also I am taking the 150. Okay, and then let's check. Wait for 20 minutes. For this 20 minutes means for this particular watch. Once you see that all the numbers get settled down, means there is a steady state comes, and then again note down the temperature. So T1 30, T2 148, T3 150, 154, 156. So as it is, the temperatures is not changed. Let's check what is the impact of on the Nusselt number and the heat transfer coefficient. So again, do the calculation. Similarly, you have to do the calculations. Okay, you just mention everything is here in this table. The metal is same, volt is same, this one is same. Only the changes is what we change the material. Sorry, we change the diameter. So you just note down the second reading is for changing the diameter. Okay, somewhere you just note it there, and then check what is the impact. You see here the heat transfer coefficient and Nusselt number. You see the Nusselt number goes down, means by increasing the diameter of the tube I found the Nusselt number is decreases. Okay, then again for your information you can do the changes for just reducing the diameter from 7 to 6. Okay, because initially again and again do the same power. You kept this 150, waited 20 minutes according to this watch. Okay, you see there is a continuous changes in the temperatures. So up to the 20 minutes you just watch it, and then it gets steady. Okay, so now here you can see 30, 148, 150, 154, 156, 36. Everything is as it is. The temperatures doesn't change. But look at what is the impact on Nusselt number. It goes increase. Now by decreasing the diameter, increase the Nusselt number. Now from that one you can understood what is the impact of the variables. When I change the variables, what will be the impact? Similarly, even you can do the this particular experiment by changing the length. Okay, by changing the thickness. Let's check it. What is the impact of it? Okay, but that is for your information I'm talking. But in our practical, what you have to mention, you have to do it for aluminum with the 7 diameter initially, whatever be the it is mentioned. Okay, and then you can either increase or decrease, take at least the one reading for it by increasing or decreasing the diameter of the cylinder. Okay, so this is the one, and in a second you change the material copper. Okay, now instead of the aluminum, now you see here the color get changed. Now it is aluminum. You can see the internal structure is as it is. You kept this reading as it is, and again okay. So now what you have to do, again do the same thing. You start the power, adjust the voltage what you initially put it. Okay, it is 150 as I taken, and then again wait for a 20 minutes according to this watch. Okay, so once it is show the 20, everything gets stopped, and then again note down what are the readings. You might be see the readings are maybe the same, but let's look what is the impact on this one. You will get the same one. Okay, and then the there is some queries comes in your mind that why when by changing the material till I am facing the heat transfer, it is the same, it is not changed. And what is the reason behind it? Can anybody tell me?
So can you repeat the question?
Yes. You can see here that I'm changing the material. I just put it, everything is constant, okay, as for the previous case, for the aluminum one. And now you see the Nusselt number is same, 78.48. Why there is no change of a Nusselt number even I change the material? Yes, anybody? Now that
Be-
questions and that queries, definitely it will stimulate your mind, and then you are thinking in that direction, what is the impact of variables, and then you can easily choose the material for your exchangers, for the cooler, for the condenser. Okay. Yes, anybody?
So because Nusselt number doesn't depend upon material.
Yes, correct, absolutely right. Nusselt number is not depend on the material. We are doing a practical on a convection one, not a conduction. If it is a conduction, then definitely it will be the impact. But as the material is not changed and we are kept, this voltage is same. So that's why there is a no impact of material on this experiment. Is that clear?
Yes, sir.
But yes, if we change the diameter, if we change the length, there will be the changes in the Nusselt number and the heat transfer coefficient. Or similarly, if I change the voltage, if I change the voltage from 150 to, say, now I change it to the 200, let's check what happened. The temperatures might be different now. Okay. And at the same time, you can see here, sorry, I again reset it, the part, and let's check what happened to there. Yes, I just on it. I kept the material aluminum as it is. Okay, no problem. I just change this voltage up to the 200, and then let's check what is the impact. So let's see what is the impact of by changing the voltage, because the Q get changed accordingly. Definitely, it will have some changes. There should be some changes. Now, yes, you can see here there is a minute change, 78.48. Now it is 78.41. Am I right?
Yes, sir.
So you can do this practically in various way, depend on your curiosity. But for our calculations, I just suggest you just choose the one or two materials here. Okay. And you choose the aluminum, you choose the copper. You can it is on you. You are free to choose the voltage, anything. Okay, from changing the knob of this one. And yes, for the two materials, you just change the diameter of the cylinder, and whatever be the results. So obviously here you might be found there is a four results. Okay. So in a in this what we call in a table, you can say you can write table like this one. The material, in the second column, you just write diameter. Okay. And then in the third column, you can write the heat transfer coefficient, and in the fourth one you can write the Nusselt number. Okay. So like that one, you just make a chart, the table, and lastly you can conclude it, result you can write here, heat transfer coefficient H for the copper aluminum is this one, the Nusselt number is this one. For